Boa tarde a todos, bem-vindos ao colóquio, recomeçando agora no segundo semestre. Eu vou trocar para inglês. It's a pleasure today to have Professor Felix Klink that's going to talk about the new experiment that's running, in fact. And he got his PhD in Arizona. Then he went as a postdoc to Fermilab. Let me see if I get everything. Irvine, then Daisy now. And I miss, pardon? And Slack, sorry, I missed this one. And he's one of the proponents of the experiment, and he's the physical coordinator for the theoretical part, and he's going to tell us about that. Thank you.
Okay, complain if you can't hear me. So at first, thank you for the invitation, and maybe a small anecdote. When I started my master degree in Heidelberg, my first week I started, Oscar was visiting, so he is actually one of the oldest colleagues I know, so very nice coincidence. So I'm very happy to be here. I'm here actually for a couple of weeks. We got a visitor grant by FAPES, so very much thank to them for sponsoring this trip and allowing me to be here. And I want to talk about the phasor experiment, give you an overview over what this experiment is doing, why it's there, what its trajectory was, and what to expect in the future. So I typically try to explain in the first few slides what's the big idea so that you have the big picture, and then later on I just fill in some details and anecdotes, and but already after the first couple of slides you should know roughly what I'm talking about. So phasor is an LHC experiment, and well, you probably heard that more than once. So the main focus of the LHC when it was designed was to search for heavy new particles. So the Higgs boson, we found it. Supersymmetric particles, well, we haven't found them yet. And these particles are typically produced in PP collisions. They're very heavy, roughly at rest, and then they decay roughly isotropically. So we build giant detectors like the Atlas detector here around it to capture its decay products. So this is, one would say, high PT physics. So particles that go, well, roughly away in the transverse plane from the collision. And this was really the design principle for both the Atlas and CMS experiment. However, there's also another region, the forward region. So this is a region in which the beam travels, so along the beam pipe. And we actually produce a huge number of particles there. So this is, in most collisions, you collide protons, they interact in some minimum bias collision, so very little momentum transfer, they break up, and you produce tons of pions and kaons. And with tons, I really mean a huge number, so something like 10 to the 17 pions, 10 to the 13 beam mesons within 1 milliradian around the beam. A milliradian is the size of the moon on the sky, so a rather small angle. And just as comparison, we produce 10 to the 7 Higgs bosons at the same time. So this is like 10 orders of magnitude more. So pretty large numbers. And these particles can be very energetic. So idea being that, well, the beam breaks apart, its energy has to go somewhere. And where does it go into? Well, into the pions and kaons and other light hadronic particles. And these go down the beam pipe. Well, we don't probe them for two reasons. Well, first, we didn't think that they would be particularly interesting. Also, we can't really put any detector there because, well, we need to let the beam in and out. Otherwise, we don't have any collisions at all. The question I asked myself as colleagues is, can we do anything with them? So high energy, large number of pions and kaons. And the answer is obviously yes. Otherwise, I wouldn't be standing talking about it. So one thing we could do is that these particles, pions and kaons and d mesons, they can decay. For example, in neutrinos. And this gives us then a strongly collimated intense beam of TeV energy neutrinos. And that's interesting because, well, we don't have any other lab that produces TeV energy neutrinos. So that is sort of nice opportunity. If you come from BSM physics, so look for new physics, then you would say, oh, well, maybe these particles can also decay into one of my favorite candidates of new physics. So for example, dark matter, axion-like particles, dark photons, heavy neutral leptons, stereo neutrinos, whatever your favorite candidate is. And even if the decay branching fraction is rather small, so let's say 1 in 10 to the 10 pions decays into one of these new particles, well, you would still have 10 to the 7 of them. So you could still have a dark matter factory in the forward direction effectively. Okay, so that's why this could be interesting. How could we probe this? Well, I mean, they don't go through any detector. Atlas has a hole there to let the beam in and out. Actually, the LHC detectors are really perfectly designed to not see this stuff. But if we look at the LHC, roughly speaking, it's a circle. So it will curve away. And these things are neutral, so they will go straight in one line. And the idea we had is to put a detector right here. So after the LHC curves away, put some detectors there to see the neutrinos interacting, see the dark matter interacting, see the dark photons decaying. Yeah. Okay, and we called this phasor the forward search experiment. It was done by 4 theorists. It was actually sort of how you imagine theoretical physicists to work. After lunch in a coffee break, we draw something on the whiteboard and build up the idea, and that's what came out of it. So stereotypical theoretical physics. Why called phasor? Well, there is a story that our senior member went to the Star Trek Museum in Seattle, and he saw this here, the phasor gun with PH. And we were looking at the time for an acronym that starts with F for forward, and he thought, let's call it phasor. And yeah, so it recalls another marvelous instrument that harnessed highly collimated particles and was used to explore strange new worlds. That's a footnote in the original paper. Okay, so what came out of this idea? This was just 4 theorists writing a paper, so more often than not, that ends up in nothing. It will just be forgotten, but this wasn't forgotten. So the first thing we did is we looked, well, is there any place where we could actually access this beam, where we could put the experiment? So we started looking at a map of the LHC. So this is what we found after a few-minute Google search. And we looked if there might be a conveniently located side tunnel somewhere. So the best points is here where CMS is or where Atlas is, because the highest intensity. There are not so many tunnels on this side, but on this side you see there are all sorts of tunnels here. So we look closer into that. So we use the CERN version of Google Maps, and we get this here. So Atlas is here, and then this tunnel here. So this is the LHC tunnel. So you see its curvature if you zoom out far enough. You also see the SPS. So this is a pre-accelerator. So you first accelerate protons there, and before you shoot them in the LHC. And you also see this side tunnel here where during the time of LEP, so the electron-positron colliders that were injected here, this is actually not used anymore. They built a bigger tunnel now. But this is really interesting because, I mean, where do the particles go along this beam axis, so along the tangent line of Atlas? So they just go along a straight line, and this straight line intersects with 2 existing tunnels, namely this one here and this one here. And these tunnels were, well, they're unused. So these were injectors doing that, not used anymore. So we were really excited. So then we sent someone down, Mike Lamont. He is now the head of accelerators section at CERN. So he went down and he took this picture and said like, oh, look, there's nothing really standing there. Looks pretty dark. Went a bit further. Saw this, tunnel ends somewhere. What's written there? Door definitely closed, cannot be used as emergency exit. Okay. But we don't care what's behind this place here where this is really what we needed, and that it's closed is actually good, so no one might need to use this as emergency exit and come this way, so it's we're not blocking any emergency way. Okay, so great. So in principle, we could put something here. we then ask, okay, where exactly is a beam? And of course, I can't really predict that, but CERN has a survey group that can map where the beam goes up to millimeter precision. And they have done that, so they drew this here on the ground. So it turned out that it's, well, it actually goes through, but it was a little bit below the floor. So, so we ask ourselves, how close do we want to be to this beam axis? And this, okay, this is way newer simulation, but it still shows it very nicely. This is a muon neutrino beam, so electron and muon neutrino beam in like the transverse plane at this location. It's roughly 500 meters downstream of Atlas, and you can see it's all of 10 centimeter wide. So the neutrino beam is actually super collimated. It's 500 meters away, but it's still only this size. So if you want to build a detector, you really want to align it with a beam that's this size. You don't want to put it like a meter away, right? So, well, what do we have to do? Our plan was, well, we built a trench. So we lower the floor a bit. It's just concrete. Concrete was easy to remove. Removing the rock would be difficult because, well, they were built in the 80s, and everyone who knew what the rock and geology was is probably long retired, but concrete wasn't so tricky. So this was our technical design. So we found some experimentalists that thought that would be a good idea, and who then planned that. And this was our plan in 2018, I think, so about a year after we wrote the theory paper. Okay. Actually, this was then realized. So there was a, well, it's on the, so on the LHC on this side is the walkway, on this side we are, so they built this thing here so that we can transport ton detectors over the LHC, and even if we let it drop, we wouldn't break it. And then they started to dig to create this trench here that then allowed us to put the detector right on the aligned with the beam. Okay, so how would the detector look? So this is, I'm a theorist, by the way, so this is my view of how detectors work. I designed them in PowerPoint. So our first motivation was actually new physics. So we look for decaying particles. So our prime example is the dark photon. I will tell you later what that actually is, but the idea is that the standard model has particles that are long-lived, for example, the pion or the kaon. They can travel many meters and then decay. So, but we are, for new physics, we are mainly looking for things that decay more or less immediately. So maybe the reason we haven't found anything is because the new stuff is also long-lived. So a long-lived particle, and the dark photon is one example of this, and it would mainly decay into electrons, just to be concrete. So what would be the signature? So you have a dark photon coming from the left, being produced at Atlas, have a beam that's roughly this big, so order 10 centimeter, and then this thing would decay. I mean, it's TeV energies, so you would get like TeV electrons. They would be strongly collimated because the mass of the particle, well, comes from pion decay, can't be too heavy. So what we thought is, well, let's put a magnet there to split the two tracks so that we at least know it's two. Let's put a tracking system there, because if we want to say there are tracks, we better have a tracker. Also has the advantage now we can measure the curvature, so we know the momentum. Let's also just put a calorimeter here, because it's always good to have a calorimeter at the end of the detector. And let's put a shield in front, just to be sure that there is nothing coming in that we are not aware of. So, for example, a muon that could create some activity. We don't want that. So this was our design. Later, we also thought about neutrinos interacting, and we said, well, let's put a neutrino detector there. I mean, here we have a decay volume. It's empty, so neutrinos don't interact in empty, but you want to have as much mass as possible. This is what this is for. And it's, as you will see later, neutrino detector really designed to see the details of the neutrino interaction like a proper neutrino detector should, with more scintillators in front to make sure we know that nothing else came in. Okay, so this is my theorist design of how this experiment should look. Let's see, this is what the experimentalist made out of it. So It looks, of course, way more sophisticated, but conceptually it's really the same. So we as theorists did a good job designing this detector. So now the beam comes from the other side. Here we have a neutrino detector. It's an emulsion detector. There are plenty of scintillators. There is magnets that are hollow in the inside so that particles can decay. We have 4 tracking layers. They were donated by Atlas. This was their spare modules for their inner tracking system that were still lying around in various institutes, and we collected them all and put them there. So that made this part of the detector very cheap, of course. So we have a calorimeter at the end. This was spare modules from LHCb. They were very happy to give them to us so that they don't stand in their basements anymore. So this is the detector we planned, and this is the detector we built. It looked basically the same, except that there are much more cables sticking out so that you can't really see anything anymore. But well, you can see the electromagnetic calorimeter at the end, and here you can, well, with a little bit of imagination, see the magnets. Okay. So the detector is there now. It started operation in, well, beginning of run 3, so in 2022. So it was constructed during the pandemic times and has been operating now for a while. Okay, so let me tell you what we did. And well, I promised you at the beginning we would do new particle searches and we looked for neutrinos, and we did both of it, and I will show you some results. So new particle searches, what are we really looking for? Well, one motivation, my favorite one, is dark matter. So we know we have a standard model, you and me are made out of it, and we have probed it rather extensively in all sorts of experiments during the history of particle physics. We're also pretty sure that there's something called dark matter, so some matter that we can't see, so it's dark, but it's out there and causes rotation curves to look different than what we would expect otherwise. And as a theorist, what we would like to do is, well, we would predict how much dark matter there should be. We have seen there's 5 times more dark matter than visible matter. But to write down any sensible model where we could make any predictions, you typically want some interaction. I mean, you could also say, that's just some outcome of string theory and something at the Planck scale and otherwise uncalculable, but that's also not a very predictive model for a theorist. So it's better to postulate some other interaction. And then you could make assumptions like there was a thermal equilibrium between dark matter and the standard model matter in the early universe, and then there was thermal freeze out, and then we can calculate what's the amount of dark matter that's left. Okay, so pretty standard. I mean, this is the same story for example, WIMP dark matter or most of the other popular dark matter candidates. If you like WIMPs, you would have a well, you ask, okay, what could this mediator be? And you would say, it could be the Z or the Higgs boson. So some mediator that has like weak scale couplings and weak scale masses. We're more interested in light dark matter, so something that's more like below a GeV. And Audie, Lee, and Ryan work in 77 showed that if you want to have such light dark matter, then you can't use the Z or Higgs boson anymore because its couplings are just too strong. You would end up with way too much. Okay, but what people do is say, well, if we can't use the Z, then let's use a new particle like a Z prime or A prime, now called the dark photon. So the idea is simply to have a mediator that's lighter than the Z boson and that's more weakly coupled than the Z boson, that then is able to reproduce the amount of dark matter, the relic abundance that we observe in the universe. Okay, so how would that look for us? So the dark photon, actually it arises in many models of hidden sectors. So some new physics that describe the dark matter sector. And it wouldn't be surprising if that's more complex, right? The standard model is super complex. We have like fermions and quarks, we have electromagnetism, the weak force QCD, 3 generations of all of those. So why should be dark matter just be one particle and nothing else? So it could have a sort of dark version of electromagnetism, and this could be broken, so it could even be massive. And what's interesting is if you would have such a photon of the dark sector, so a dark photon, it can kinetically mix with our photon. So you could have a diagram like this, or in the Lagrangian formulation, you could have that the field strength tensor of our photon and of the other photon, they can mix. That's the dimension for operator. So it just describes the mixing. Well, what we do then, essentially everywhere in physics, is if we have such off-diagonal term, we diagonalize some matrix, and effectively what that means is that we could shift this mixing here that would induce couplings of the dark photon to the charged fermions. So this new dark photon would actually couple two charged fermions, and the mixing is small, epsilon. Like everything in mass that's called epsilon, this epsilon must be small. So it would get a small coupling to charged fermions. So that's our dark photon. How would it look like in the detector? Well, it could be produced in any way we can produce photons, as long as kinematically possible. So for example, pion decays. So pions typically decay to 2 photons. This one could decay to a photon and a dark photon. Branching fraction would be sort of order epsilon squared. So if we want to have one decay in 10 to the 10, then epsilon would be order 10 to the minus 5, just to give you a feeling. It could decay into charged fermions. So for example, electrons. The decay width is proportional to epsilon squared, so small. That means the lifetime is long, so it could be a long-lived particle. So exactly what we wanted. So great candidate for what I want to demonstrate. How does it look in the parameter space? So this is the mass of this particle. Here's the coupling. There are various existing constraints here from resonance searches and from other long-lived particle searches. And the region that we could probe is this red region here. So for different luminosities, so how long we run the experiment. And you can see we can bite a bit into this otherwise unconstrained region in between. And that's exactly the region that is motivated by our motivation in the first place, so dark matter. So if we want to reproduce the amount of dark matter we observe, we want to be somewhere on this line. I mean, we needed to make some assumption to put this line there exactly, but it's not unreasonable assumptions, and typically this line is somewhere in this region. So great. This is what we aim to do. And then after we built the experiment, we went ahead and did it. So we looked for dark photons. So this was our first analysis. So we tried to be super conservative and well, not end up with an analysis where we see a lot of backgrounds. So what we looked for is, well, collision events where we see nothing coming in, and then 2 tracks appearing and depositing a lot of energy. So this was our analysis strategy. If we estimated that there should be like order 10 to the minus 3 events from rare neutrinos interacting somewhere in the detector components in between. Doesn't happen very often because they're rather light. And then we did the analysis, and unfortunately we didn't find anything. So would of course be great if we would have discovered a new particle. You would have probably heard it in some popular news, but we didn't. So what we could do is we can place a limit on this dark photon, and this is shown here. So we probed some new parameter space, especially the motivated one around this dark matter relic target line, so the cosmologically motivated parameter space. Okay, so this is just one analysis, the first analysis we did. There are, of course, many more models of long-lived particles. I mean, here I just had a nice figure that I made with all the models that have been investigated in the context of phasor, and how they are motivated by all the big problems of particle physics, dark matter hierarchy problems, strong CP problem, neutrino masses. Even as a candidate for a light inflaton, someone wrote a paper on that. So there are many more models that we can look for, and we had more analysis. Actually, this one here is a rather recent one where we looked for axon-like particles oh, this is the wrong link, sorry. Where we constrain some of them as well. Okay, So let's go on to the next topic. So if you're not interested in hypothetical particles, you might be more interested in neutrinos. They do exist. That's a great advantage. The idea of looking for neutrinos at a collider is actually rather old. So the first one thinking about it was Alvaro de Ruyula in 1984. And he wrote a paper, I can't really read it, but it was called Detecting Neutrinos at Future Colliders. And it was about the LHC and the SSC. And it was a time where papers were still written with a typewriter and formulas were still added by hand. So he already thought about it, but then every decade there was like 1 or 2 papers on this idea, but nothing happened on the experimental side until 2018, when we started to investigate this location here. And what we did is we put a small detector there that was mainly meant to measure the background levels, like how many muons are there. But it was actually also a neutrino detector, so the people who did the background measurement were neutrino physicists and already built it so that you could maybe also look for neutrinos. And this detector was super tiny. I mean, it's like a box, like a sort of lunch box or a small carry-on luggage sort of. It was 10 kilograms filled with lead and emulsion. Emulsion is what they used in Opera and Donut as a neutrino detector. It's a great advantage. It's analog. You don't need any power supply. You just put it there. We left it there for 4 weeks and then analyzed it. And we actually found, I think, 6 neutrino candidates in there. It was like 2 point something sigma evidence. So here is probably the first neutrino interaction at the collider ever recorded. And just to give you a feeling, so this is a slide my colleague Jonathan Feng did. All the previous collider detectors, like the big ones like ATLAS, CMS, D0, the ones at Lab, these are all like building-sized detectors. I mean, ATLAS would not fit into this building, cost billions of dollars, decades of operation, and altogether they found 0 neutrino candidates. And then you have this tiny little thing, like a suitcase size, run for 4 weeks. It was made of a recycled part of another small-scale experiment, NA65, that you've probably never heard of. And that little thing found 6 neutrino candidates. I mean, that's pretty amazing and just shows the advantage of putting a detector at the right place, namely in this forward direction, right into this neutrino beam. Of course, this is not yet real physics. We haven't really measured anything with any significance, but actually now 2 neutrino experiments to exploit this. So one is the one that I've already showed, the phase experiment I work on. There was another group of people, they were also around the same time investigating the idea. They looked at various places, more close to CMS actually, but then they saw that we proposed this location, and they thought, that's a very good idea, so how about the other one? So then they also put the detector there. This one is on axis, this is a bit off axis, so they're like half a meter besides the beam. This has a magnet, this does not, but therefore it has like a sort of dense muon system, hadronic calorimeter. So there's some complementarities, both in physics and detector technology, so it's actually really great to have these two. We learned a lot from each other, from our successes and mistakes. For example, that being on axis is actually really good because you have more events, so that's one thing that we certainly learned. Okay, and then we said, okay, now the next step is to really observe these collider neutrinos. And the first thing we did was actually something really simple. We said, okay, let's forget about the neutrino detector. This is an emulsion detector I will show in a moment. It really takes a long time to look for stuff there. Let's do something simpler. Let's just look for neutrino coming in, interacting, and essentially a muon coming out. So it's a muon-neutrino interaction. So we just look for muon appearance. So one of the simplest things you can do in a detector is look for muon appearance. So front veto off, and then everything else fires, and you see the muon track. Okay, and this only uses the electronic parts of the detector, so it's relatively simple to do. So we use the 2022 data, so that's roughly 30 inverse femtobarn for the collider physicists in the room. And what we looked for is, well, something that didn't activate the front veto and gives us one nice track that has a high energy of above 100 GeV. So what are the backgrounds for this? So this is a figure that sort of illustrates it. This is a momentum, and this is a transverse position. So how close are you to the center or the edge of the detector? So edge is up here, center is down here. And roughly speaking, we see that there's a population of backgrounds of muons coming in from the sides, scattering, and then sort of looking like they come from the central part. Of course, that only happens either if you're close to the edge or if you have a low momentum, and then it's more likely that you change your direction more by scattering. But at high momentum and from the central part of the detector, we don't really expect to see anything. Okay, so this is our signal region here. So this is where we expect neutrinos to be, and we estimated there should be like point something plus minus 1 events in there based on our background estimate. But the challenge really was to provide an estimate here, so it's probably terribly pessimistic or conservative already. And then we unblind it, whoop, and you see, ooh, there's a population of events here that looks clearly a bit different than this one, but it looks exactly how you would neutrinos expect to look. It's actually 153 neutrino events over like less than 1 background, so that's a 16 sigma discovery, so probably one of the highest significance discoveries that have been reported in a while. Of course, what does 16 sigma mean? It becomes statistically sort of meaningless at this stage, but it really is a nice first discovery of collider neutrinos. Okay. Our colleagues from the other experiment also saw neutrinos roughly around the same time, so there was a bit competition. The idea was basically the same, so nothing comes in and the muon track comes out. They don't have energy, but they have this dense muon system here, so a muon is something that makes it to the end. And okay, they also did some background estimate, and they found 8 events. So the reason why the number is smaller is because they are off axis, so they are further away from the beam. Remember, the beam was like this size. They were over here, so they had a bit of a disadvantage because of that. Okay, and then I mentioned we actually have a fancy neutrino detector. This is an immersion neutrino detector. Immersion is photoplates, and if you look at the physics textbook, like discovery of the pion, that was done with like immersion films, so photoplates where you see the tracks in the nuclear immersion films. So rather old technology, but it's still working. Its great advantage is that it actually has sub-micrometer resolution. The great disadvantage is that it's a photofilm, not a video film. So if you leave it there for months, then you have all of the data from 1 month on top of each other. So these photofilms were interleaved with tungsten plate. Tungsten is the heaviest affordable metal that we could find. And it gives roughly 1 ton. Here you see a picture of it. So we have like 700 plates of tungsten interleaved with immersion. We left it there for, this is about a month in 2022, and analyzed 100 kilograms of it. So that's about 1% of the data we have collected so far. It's just our first analysis. Then what you do is you take out the immersion films, you take a bunch of students and let them develop the immersion films in a dark room for a couple of weeks. Then you take these developed films and send them to Japan, where you let another couple of grad students scan the immersion films overnight for a couple of months. And then you take the digitized data with like billions and billions of points and connect the points, so do some tracking. And then in this big mess of tracks, you look for neutrino-like events, so when nothing comes in and tracks go out. So it's really like looking for the needle in the haystack. And then you try to, from the neutrino events, measure momentums using multiple Coulomb scattering, or look for electrons with electromagnetic showers. So you see, this is a non-trivial procedure with many steps, and it's amazing that people can do that, but there is a community of people that spends all their career doing this and optimizing this. And I will show you on the next slide one of their events. And what we have seen is 4 electron neutrino, 8 muon neutrino candidates in this subvolume there, and each of them like 5 point something sigma discovery of those. Okay, so here, as promised, is one of those events. So this is how it looks from the side. Nothing comes in, and a bunch of charged tracks come out. So these colorful lines are charged tracks. I don't think the colors really mean anything. That's just the way they're plotted. This is sort of the front view. So the neutrino sort of comes out of the wall, and you see that there's an electron here recoiling a bunch of other things. So this is the hadronic activity of a neutrino interaction. So neutrino hadron or neutrino proton goes to electron plus a bunch of pions, kaons, God knows what. And you see a lot of details, like the density of the shower tells you something about the energy of the electron. The amount of wiggling around tells you something about the momentum of the tracks. High momentum tracks are straight, low momentum tracks wiggle around a lot. You can count the number of tracks, and keep in mind this is like 100 micrometer here. So this is really high precision. So we can learn a lot about these events. Okay. This actually got quite some attention. So of course, all our member institutes had a press release, and I think my favorite one is this year by Elizabeth Rochester. I never met her. She has nothing to do with phasor, but she was asked to write a Viewpoint article, and she called it the dawn of collider neutrino physics. I think it's a nice description. I mean, we have for the first time now observed neutrinos at the collider, and the question is, what can we do with it? And the answer, as I will show you in a moment, is actually quite a lot. Like every time we find neutrinos from a new source, we typically learn something quite interesting about either the source or about neutrinos. Okay. So what can we do with it? I mean, we can either learn something about the source, so their production, or about neutrinos, or use them sort of as well, study their interactions. So where they're produced in, well, I told you pions, kaons, d mesons. So actually, this has not been measured very well. So we learned something about light and charm hadron production. Or we use them either measure the cross-section energy regime where we haven't measured it, or do what we already did in the 90s and use them as to probe deep inelastic scattering, so to probe nuclear structure, for example. Okay, so let's start with where do they come from? I know this is a terribly messy plot, so let's walk you through very slowly. So this is electron and muon neutrinos. This is the energy, and this is the number of interacting neutrinos plotted as a histogram. And then the different colors here are neutrinos from kaons, from pions, and from charm decays. So we can see pions only decay to muon neutrinos, but not electron neutrinos. You remember there was a chiral suppression argument that you might have had in some particle physics course. Kaons can decay to both. So kaons dominate the electron neutrinos and also the muon neutrinos at high energy. And then there's also charm decays that can also decay to both. They reproduce less charm quarks, but they're more likely to decay. Pions typically get absorbed before they decay. So this is where the neutrinos come from, and then you have these different line styles here. So this is different models, generators, different modelings. You can see kaons, well, we can roughly describe pions plus minus factor 2. So not too good, not too bad. I mean, factor 2 isn't that great, but it's also not that bad. But charm is like more than order of magnitude uncertainty when I made the plot. I mean, that's probably the worst prediction for the LHC that has ever been made, plus minus 1 order of magnitude. If you're interested in Higgs bosons, there are people calculating it at next to leading order with like 1% precision or something. This is a factor 10 or more. So this is really bad. So I was a bit unhappy when I made it, but then I asked myself, why is it so bad? And then I understood, and then I realized that there's actually all these reasons why it's bad, like PDF uncertainties, hadronization uncertainties. These are things that we can end up constrained with it, so we can learn something about all these sources of uncertainties that go into this plot. I will show you maybe already on the next slide. Yes. So here's one example. I took so on the left is my favorite prediction, and on the right is sort of the worst prediction. And we have done in the December of last year a measurement of the muon neutrino flux using the electronic analysis, so the muon appearance analysis that have measured the flux. And you can see, so this is for muons, antimuons, and some very high energy bin where we weren't sure anymore. And you can see that my favorite sort of modeling describes this actually pretty well. I mean, within like a typical uncertainties. Okay, we have a little bit of an excess here, but otherwise it's fine. This here, so this model here, it's called DPMJet. That would actually predict the huge excess of neutrinos from charm decays at super high energies, and we see that's not there. So you can actually already say that this model is ruled out. So great. So we have already learned something, namely that this model is not true, or any model that would like it would look like it would also be ruled out. So we actually start to constrain forward production models with it. And when I made this plot, we had no clue which of these would be right. Now we have the first data. And this will just improve in time. We will start to have electron neutrino measurements. We will start to have more bins, smaller statistical uncertainties. So this is one example of what we can learn from collider neutrinos. What's the underlying physics? So one of it is PDFs, so parton structure. So this is a typical landscape of it. And if you look, or if you calculate what is your, or where does your charm production come from, it's a gluon and another gluon, and they collide, and they produce two charm quarks. And one of it has to be very energetic to give us a high energy neutrino. That tells us one momentum fraction has to be order 1, and the other one has to be very small, 10 to the minus 6-ish. So one is here, the other is here. And you see, oh, there's no other measurement in this region here. So it's actually a proper unique region of parameter space of proton structure with these measurements at very low x. So this is for the experts in the room. One might be sensitive to gluon saturation, or this high X region sensitive to intrinsic charm. So properties or phenomena that have been predicted but never been observed that are still somewhat controversial that we could start to test with these measurements. Okay, let me just say a few words. Another community that's interested in these measurements is the cosmic ray community. The idea being that a cosmic ray collision is pretty much like a collision at the LHC, just that you don't look in the center of mass frame, but in the fixed target frame, so where one is at rest and the other one comes and collides. And the cosmic ray people, they have a problem. They see an excess of muons that come out of these collisions, out of the air showers. That's actually pretty bad excess. This is 8 sigma or so compared to their models. So their models are not very good, and they want to resolve that. And one hypothesis they have is we could resolve that if we produce a few more kaons. That would resolve it. They can ask me later why. I'm happy to tell you the entire story. And if this hypothesis would be true, so this is a toy model where we tried that, and then at the collider, it would actually lead to a huge excess in neutrinos, in this case electron neutrinos, at phasor, which well, we should be able to see pretty early. So this is a model we can rule out as soon as we look at the first electron neutrinos. I mentioned forward charm production. So if you talk to your colleagues at IceCube, they would call forward charm production their prompt atmospheric neutrino background, and they have large uncertainties on it, mainly coming from PDFs. So constraining those, so constraining charm production at colliders also constrains it there. And then the uncertainties are lower, so the prospects for analyzing the astrophysical neutrino signal would become better. Okay. Can also do neutrino cross-section measurements. So our first measurements have actually already contributed to this. So previously there were measurements at accelerators, so for example at Fermilab, some by IceCube at very high energy, but this TeV energy range was unprobed, and we started to fill this with both immersion and the electronic neutrino measurements, so the muon appearance measurements. So we have first measurements of neutrino cross-section at TeV energies, and they're in agreement with what we would expect. Still large uncertainties, but they will get better with time. You can also ask, okay, this was a total cross-section. We can look at it differentially, so we can look at deep elastic scattering and essentially use these measurements as a neutrino-ion collider. I mean, our target is an ion, tungsten in the case. Center of mass energy is very similar to the Planck electron-ion collider, which is also the reason why I called it neutrino-ion collider. So it's very similar physics, but instead of a photon, we would exchange a W boson, so it's a charge current equivalent. But the physics one can do is very similar. You can look at nuclear PDFs. You can look at, actually, one feature is that you are more sensitive to the flavor of the particles here. So for example, if a charm quark comes out, a strange quark must have been the initial state, so you probe the strangeness content of the proton if you can text that there was a charm hadron in the final state. And this is something that's poorly constrained, but it could be constrained with this. This is a study some colleagues did, Cruz Martinez et al. How well would PDFs be constrained with those measurements here? And they found actually by quite a bit. So red is what there was our current knowledge, and blue or green here is some projection. And then this is for the down quark, this is for the strange quark. So it proves quite a lot. And this is actually useful if you work at Atlas and CMS. PDFs are always part of your uncertainties. So this can lower the uncertainties for some of the key processes at the LHC, like Higgs or weak boson production, W mass, and so on. So it's just one of the useful things to know for any of the physics we really want to do at high energies. Okay, let me come to the end. I think I'm almost over time anyway. No, not yet, but good. So what's the outlook? So we have Phaser running now. It will run until the end of this year, mid of next year. So that's when the LHC will be shut down for a while. Then they have an upgrade for the high luminosity LHC, so to run at higher intensities. Of course, we would like to continue running too. And ideally, we would like to be running with bigger detectors. But bigger detectors is a bit complicated in like these small side tunnels built in the 80s. So what we would really like to do is to have a bigger cavern that's built for the experiments and not experiments built into existing, not so well-suited side caverns. And this idea led to the Forward Physics facility, so to create a new cavern here that with several experiments that would be placed around. So you would have neutrino detectors, either with emulsion or liquid argon. You would have a bigger version of Phaser for long-lived particle searches, another one for milli-charged particle searches, to really harness the potential for physics searches, neutrino physics, QCD measurements, input for astroparticle physics. So this is something that we would really like to do. Something that we will certainly do is we will have an upgrade of the Phaser detector to make it a bit better based on the experience we collected in the last couple of years. You could also think a little bit further, so this might be interesting for the young people in the room. So we are discussing various future colliders, and of course we can also do neutrino physics there. So if you're a fan of the 100 TeV Hadron Collider, so the FCC for example, then you can pretty much copy the idea, and you see that you have really huge neutrino fluxes up to like 50 TeV energy. And the fluxes are so big that you could start to do things like look at neutrinos from heavy ion collision, or look at put experiments there for with polarized targets and look at polarized PDFs, for example. Another great source of neutrinos is the muon collider, not because they produce many neutrinos, but because the beam decays away. So you just get a huge neutrino flux from a decaying beam. And so that's, of course, really ideal for neutrino experiments. So you could really do, neutrino ion collisions with statistics that's not too different from the EIC. So the rate of neutrinos would be in the kilohertz range. So it's that's just enormous. I mean, now we have one every minute, every couple minutes or so. That would be kilohertz. So that's like, I mean, to me that just sounds very amazing. Good, good. So what had I said? So I introduced that there is a novel forward physics program that has emerged at the LHC, especially with a phaser experiment to look for new physics, but also to study neutrinos. And it actually already has its first success. It has discovered collider neutrinos. So it's this first observation of neutrinos produced in colliding beams in over 50 years of hadron collider physics. So this is a nice achievement. But this is just the beginning. I hope I convinced you that there are many interesting things we can do with it. And I want to use the words of one of my colleagues who called it the time of multi-messenger collider physics. Of course, that's making a bit fun of the multi-messenger astronomy. So here, neutrinos would be a messenger to QCD, and new particles as a messenger to the dark sectors that we could probe with it. I'm sure there are more interesting results to come. As a reminder, we've only really analyzed like 1% of our Martian neutrino detector data. So there will be many interesting results coming out of it. And well, as a theorist, I can say theoretical and phenomenological efforts has always played a crucial role. So if you come also from this side, then have an idea, let me know. We are always open to new ideas. It's a small collaboration. I'm the physics coordinator. If I see a good idea, then I can tell the experimentalist work on it. So we can do that. If you come from the experimental side, well, of course, there are also many opportunities. So if you're interested, let me know. And now I just want to thank you for listening and, of course, for inviting me. So let me know if there are any questions.
Thank you for this excellent colloquium. We have time for questions.
Thanks for this very nice talk. It seems to me that they were always there waiting to be found. Why it took it took so long for coming out this new idea, let's say?
Good question. So I think it's, let's see, these locations here were simply overlooked. I mean, our competitors from the SND collaboration, they looked at various locations around, closer by at a larger angle, but there the flux is just very tiny. I also calculated how many neutrinos do we expect to interact in, let's say, CMS. CMS is a huge multi-ton detector, multi-kiloton detector, and the answer is like something like 20, 100, something like this, during the high Lumi LHC. It's just a tiny number. But you really need to go in the forward direction. Okay, that people kind of knew but didn't really take too serious, and you need to find the right location where you can actually access this beam. And people haven't really looked for this until we sort of, we looked more for dark photons and stumbled upon this location and then revived this entire physics, field of physics.
Since I have one curiosity. What about funding? A bunch of theoreticians proposing an experiment. How did it take place?
That's a very good, very good question. We were very lucky. I mean, my colleague Jonathan Fang, he gave a talk at, I think it was some Santa Barbara whatever workshop, so one of the workshops they have. In the audience, there was someone sitting who was a funding coordinator for the Heising-Simons Foundation. And he approached him after the talk and said, like, hey, I'm the funding coordinator from the Heising-Simons Foundation. I really like your talk. I think this could be interesting for our foundation. Would you like to be funded? For the young people in the room, this is not how it usually works. Usually you go to many funding agencies and beg to get some money, not the other way around. Well, we stayed in contact, and we got some experimentalists to work on it, and we designed the detector, and we approached them again and said, like, well, you said you were interested, so we came up with a concrete plan, and it cost order of $1 million to put this in. Are you still interested? And they said, yes, please write down something like a 5 to 10 page proposal. We did that, and they said, okay, we would like to fund it. CERN approves it, and CERN said, well, I mean, if you have funding, then we will not stop you. And then it went through with, essentially it was approved 1.5 years after we wrote the theory paper, which is amazingly fast. So being lucky is the answer.
Questions? You're shy. I have a technical question. You showed one slide that you have large uncertainty in the prediction of the new flux.
Yeah.
How can you measure something with a flux that you don't know exactly?
This is a very good question. That shows me you paid attention. Yes, that is true. So essentially, these uncertainties here, okay, in this plot, there are still statistics dominated, but the flux systematics are actually pretty much the same size as the statistics. So we used all our best knowledge and best prediction now on the flux. We refined it from this actually rather bad prediction that's like 4 or 5 years old and made a new prediction where we really put in all our best knowledge and well, we arrived roughly at those error bars. But this is assuming that our best possible theory-based flux predictions are correct. I would say it will be hard to improve on this significantly because I don't think our flux prediction will get better by a factor of 10. That will not happen. So at some point, measuring differential cross sections might be easy because then you have, so this is, for example, what you would need for here. You would look at the lepton kinematics, for example, that gives you additional information. So you don't just look at the fluxes, but also at the interaction kinematics where you can extract new information. But to measure the total cross section, it will get hard. You can maybe look at certain special processes like the fraction of neutrinos that produce a charm versus it doesn't. This is actually what the charm PDF is sensitive to. So this you could do without knowing the flux too precisely. Or you could look at rare processes like, let's say, neutrino-electron scattering, where you perfectly well know the cross-section, so you can measure the flux, and then with this flux constrain the hadronic cross-section on nuclear scattering. But these are rare processes, so you need a super large luminosity before you start measuring something with reasonable statistics. So answer is, it's not trivial. You need to be smart and find some ways around the problem.
Further questions? No? So let's thank Felix again. Thank you very much, Felix.